Hi everyone. So today we are going to look at the graphical meaning of the second derivative. All right, so pause and do the do now. So this one looks a lot like, I think this was on one of our tests. I think for our limit test, but we were using the fact that the limit as x approaches 0 of sine x over x equals 1, so we rewrote it. But actually, it's a lot easier if you just use L'Hopital's rule. So if we use L'Hopital's rule, this is the limit as x approaches 0. Derivative of the bottom is just 4. So the top we have 4 sine x cosine x minus 3 cosine of 3x. Then we can plug in 0. We get 0 here. So negative 3 over 4. So significantly easier when we use L'Hopital's rule there. All right, sorry, a lot of writing. I will provide the PDF on the lesson. So concave up and concave down. F is a function that is continuous on a closed interval, differentiable on an open. You'll notice that same thing is said all the time. F is concave up if the graph lies above each of its tangent lines. So imagine if there's my curve, if I'm above the tangent line, I'm concave up. And really a good way to think about it is it's cupped up. Right? Concave down is when my graph is below the tangent line. Right? So cupped down below the tangent line, cupped up above the tangent line. And that's what concavity means. All right, test for concavity. Let f be a function that is continuous and differentiable. If f double prime is greater than 0, then f is concave up. F double prime is less than 0, it is concave down. So basically it's very similar to increasing and decreasing, but it's the second derivative instead of the first derivative. All right, and then inflection point. An inflection point is kind of like a critical number, but it's for the second derivative. So suppose f is a function that is differentiable. If the concavity changes at the point c f of c, then it's an inflection point. So if f double prime of c equals 0 or does not exist at c. So again, it's the second derivative equals 0 or does not exist, and it has to change for concavity. So when we do like our test points, if we did like if it was like a plus plus, that wouldn't be a point of inflection. All right, find all points of inflection and intervals of concavity. So for this, we need second derivative. Concavity is second derivative. So first derivative, 3x squared minus 12x plus 9. And then second derivative, 6x minus 12. Set it equal to 0. 6x equals 12, so x equals 2. So now I'm going to, on my number line, just like before, kind of like the first derivative test, this is f double prime. Notice I always write that, and that's why, because I want to make sure I know what I'm plugging into. So here's my 2. So I'm going to plug into the derivative. If I plug in a number to the right of 2, say 3, I get a positive. To the left, I get a negative. So this is concave up from 2 to infinity and concave down negative infinity to 2. And that's it. So a good indication of this thing, like it would be concave down and then concave up, right? So that's what this thing probably looks like. All right, find all inflection points. Same thing. Pause, try this one on your own. It is a little harder. So that is an exponent. So this is going to be 5/3 x to the 2/3. G double prime is 10 over 9 x to the negative 1/3. And I'm just going to rewrite that. The cubed root of x. So my inflection point is possibly 0, right? Where does this not exist? At 0. G double prime, put the 0 in the middle. If I plug in a positive number, it's positive. If I plug in a negative, you can do cubed root of a negative, negative. So concave up would be 0 to infinity, and concave down, negative infinity to 0. And again, if you want to use less than, greater than, go for it. That's it. Show that e to the x is always concave up. So we need to find our inflection points. F prime equals e to the x. F double prime equals e to the x. Where does 0 equal e to the x? F of e to the x does not equal 0. E to the x never equals 0. So there are no inflection points. E to the x is always positive. So f of x is always concave up. Right. And if we think about the graph, right, that thing is always concave up. That's a really terrible graph, sorry. Okay, so now I'm giving you a picture. Now, notice they're asking about f. They're giving you a picture of the first derivative. So this is the first derivative. And then the red one is the second derivative, right? So first derivative, second derivative. But they're always asking about f. That's important. Pay attention to that. All right, so pause and do these four. So critical numbers are where f prime equals 0. So we get x equals 0 and x equals 4/3. Where is f increasing? F is increasing when the green is above the x-axis, so that's negative infinity to 0 and 4/3 to infinity. Decreasing is where f prime is less than 0, so that's 0 to 4/3. Does this thing have a relative max? So remember, relative max is on the number line. Does f prime go from plus to minus? At 0, this thing goes from plus to minus, right? Because it's above and then below. X equals 0 is a relative max. Right, same set of problems, we just have some more questions. So again, f prime, f double prime. Does f have a relative min? So this is where f prime equals 0 and changes from minus to plus, right? Because a negative slope to a positive slope gives you a minimum, and that's happening at x equals 4/3. All right, now where is f concave up? So now we're looking at the second derivative. Concave up is where f double prime is greater than 0. So look at that picture. Where is it greater than 0? Well, 1 and then above 1, so 1 to infinity. Concave down would be negative infinity to 1. And then the inflection point would be 1. Now, notice 0 is not an inflection point because it does not change sign. It's concave down and then concave down some more. So while f double prime equals 0 at 0, it's not considered an inflection point. And that is it. All right, I will see you on Tuesday. Have a great weekend.